Hello, this is Calc 1 by Dr. Oz. This is the fourth video in a series of four, so it's the last video. So we're going to talk about finding the area by the limit definition. Let's start. All right, let's consider a curve y equals f of x. That's a continuous non-negative curve. That's enclosed by the vertical lines x equals a and x equals b. And as well as the x-axis here. So we're talking about the area of this region here, and we want to find that area exactly. All right, so first we're going to approximate the area of the region by dividing the interval AB into sub-intervals. Let's say like I find the width of each sub-interval by looking at the difference of the endpoints divided by n. So that means I have n sub-intervals and each are coming with equal length of delta x. I call it delta x. In the next step you're going to see that. So once you have this discretization of the interval AB, so essentially you have x0 to be the left-hand point. The next point in the list is going to be a plus the length of that subinterval, which is 1 times delta x. The next person is going to be a plus 2 delta x, and all the way to a plus n times delta x, but delta x is b minus a over n. When you cancel n's, you have a plus b minus a, that's equal to b. Okay, that's why you got b here. All right, so we know that we have a continuous function on closed intervals, and we should have the minimum and the maximum achieved. So I'm going to call f of m sub I to be the minimum of the function value in the ith subinterval, and f of capital M sub I to be the maximum value of the function on the ith subinterval. Okay, so let's say like this is the ith subinterval. You have the minimum achieved here, maximum achieved here. So I'm going to use these two values to find the inscribed and circumscribed rectangles. In fact, the inscribed rectangle comes with the height f of little m sub I, and circumscribed rectangle comes with the height f of capital M sub I. So we're going to use this logic here to sort of like approximate the actual area. As you see that the area of the inscribed rectangle is f of little m sub I times the width, which is always delta x in this case. And the area of the circumscribed rectangle is f of m sub I times the width, which is again f of m sub I times delta x. Okay, so we know that the area of the inscribed rectangle is less than the area of the circumscribed rectangle. So that's one quick observation. And since we have n subintervals, for that reason we have n inscribed and n circumscribed rectangles. So we're going to take the sum. Okay, so well, this is the area of the ith inscribed rectangle. So I runs from 1 to n. So I can write the area of the inscribed rectangles with the sum, and I can call this sum to be a lower sum, to be the lower sum, and represent that by little s of n. And also we have the area of the circumscribed rectangle of the ith subinterval, right? So we have n of them, so we have n circumscribed rectangles. So this sum here represents the area of the circumscribed rectangles. I call it like upper sum and represented by capital S of n. All right, so this picture explains everything. So the picture in the middle, as you see, this is the actual area between the curve and the x-axis. And the picture on the left tells you about the area of the inscribed rectangles. That should be less than the actual area. And on the right, you have the area of the circumscribed rectangles, whose area should be greater than the actual area. So the lower sum is less than or equal to the area of the region, and that is less than or equal to the upper sum. So if you increase the number of rectangles in the sum, so the actual area is going to be squeezed better by the lower and upper sum. All right, let's quickly go through an example. We have f of x equals x squared, and we're looking for we're trying to approximate the area by using inscribed and circumscribed rectangles. and we have the area enclosed in between x equals 0 and x equals 2 vertical lines and the x-axis. Okay, so here we go. So this is sort of like the outlook of the region. But before doing that, let's first try to come up with partitioning the interval 0 and 2 into n subintervals. So that's achieved by subtracting the endpoint, so 2 minus 0 divided by n. So as you see that, delta x, the length of each subinterval, is going to be 2 over n. So going back to this picture here, so in this particular case, I have 1, 2, 3, 4, 5 subintervals, and then here as well, 5 subintervals. So in this particular case, n equals 5, so that each subinterval comes with length 2 over 5, but I'm going to keep n here as a variable so that I can play with it at the end. Okay, so this is just a representation of n equals 5 case. So as you see that, to find the areas of inscribed or circumscribed rectangles, we should go with either left endpoints of each subinterval or right endpoint of each subinterval. So for the inscribed case, let's say like if you're considering this subinterval, I'm going to go with left endpoints. Okay. For this subinterval, I'm going to go with this left endpoints. For the circumscribed case, let's say for this interval, I'm going to go with the right endpoints. For this interval, I'm going to go with the right endpoints to determine the heights of those rectangles. And here's the reason of that, because we have a function increasing all the way, f of x equals x squared. So the minimum and maximum achieved and at the left endpoints and right endpoints of each subinterval respectively. That's why we're using left and right endpoints for an increasing function. If you had a decreasing function, this could probably flip. Okay, so then we're going to look at the left endpoints here. So it's like 0 plus I minus 1 times 2 over n. Essentially, it means that if I starts from 1, for example, then m1 is going to be 0, m2 is going to be I equals 2, 2 over n, which is delta x essentially, right? m3 is going to be equal to 2 times 2 over n. So as you see, like this goes on and on. And if you go with the right endpoints, you change this I minus 1 to I here, and when I starts from 1, m1 is going to be just 1 times 2 over n, which is 2 over n, okay? And then m2 is going to be 2 times 2 over n, and on and on and on, okay? All right, let's first write the lower sum. That's essentially little s of n. So we're using little m sub I. So f evaluated at little m sub I as the height of inscribed rectangles. Multiplying that by delta x is going to give you the area of the ith inscribed rectangle. And if you take the summation from 1 to n, you're going to get the lower sum. Okay, so that's in fact represented like this. And then if you just use the description of the function, remember that f of x equals x squared, as you see that. So f of this input is going to be squared here. So square of that term times 2 over n is in fact what we're looking for. All right, at this stage, we want to expand this out and then see what it looks like. And it's done in the next slide here. So if you expand everything out, and it's going to be like I squared minus 2i plus 1 times 8 over n cubed. And we're going to use the summation properties to simplify this sum. First of all, this sum, the index of the summation is I. So this 8 over n cubed is a multiple. So we're going to pull that out. Okay, once you pull that out, you have 8 over n cubed, the summation from 1 to n, I squared minus 2i plus 1. But as you see that you have the difference or sum of some terms, so I can split this sum into 3 different sums. So one sum is going to be I squared, the other one is like 2 times I, and the other one is 1. And I keep the sign in between those terms here, as you see. And for each of those sums, I have a formula, the summation formula, and let's just try to sort of like utilize those. So the sum of I squared, I start from 1 to n, is given by this formula. The sum of I is given by this formula, and the sum of the constant here is just constant times the upper bound, that's n. Okay, so watch the second video or go back to earlier slides to see how we jump from here to here. All right, so expanding this out, and this out, and then adding them all under a common factor, we get this final result, okay? And then you can simplify that further because you have n cubed here, so essentially it's 8 over 3 after you expand this out, right? So in other words, 4 over 3n cubed, 2n cubed minus 4 over 3n cubed, 3n squared, and then 4 over 3n cubed times n. So if you simplify them all, you get the lower sum to be depending on the upper limit in the summation. All right, in this slide, we're going to write the upper sum represented by capital S of n. So this time, we're going to use f of capital M sub I. And these are the heights of circumscribed rectangles, and then this is the width of each circumscribed rectangle. So this times that gives you the area of the ith circumscribed rectangle. And if you take the sum of those areas, so you get the upper sum. Okay, let's try to sort of like write that out clearly. And in the previous slide, we just know that the right endpoints are represented by 2i over n. So we're going to look at f of 2i over n times 2 over n. Okay, so well, f of x equals x squared. So that means f of 2i over n is 2i over n capital quantity squared times 2 over n. So let's just rewrite that as 4i squared over n squared times 2 over n. So in the next step, we simplify that. Okay. Well, this is 8i squared divided by n cubed. But 8 over n cubed has nothing to do with this index I here. So I sort of like isolated that from the I term so that I can pull it out. Pull it out of the sum. So I can write this as 8 over n cubed, the summation of I squared. And use the summation formula in the second video, that the sum of the squares of the numbers would be represented by n plus 1, 2n plus 1 divided by 6. Now let's expand this out real quick. So you have n squared plus n times 2n plus 1. So I first expanded these two. And what is n squared times 2n plus n squared plus n times 2n plus 1? Well, 2n cubed plus n squared plus 2n squared plus n, right? So this whole thing here, this whole top here is in fact what this is. So 2n cubed plus 3n squared plus n divided by 6. So in the next slide, I'm going to write it clean. 2n cubed plus 3n squared plus n, 4 over 3n cubed. And now I'm going to sort of like expand this out all the way. So 4 over 3n cubed times 2n cubed is 8 over 3 plus 12n squared over 3n cubed. That's 12, well, 4 over n. And then the other one is 4 over 3n squared. Okay? So let me just write this all clean in the next portion here. So the upper sum can be represented by something depending on n, okay? So this way we found the lower and upper sum. So in conclusion, I can write this inequality here that the lower sum, is less than the actual area, which is in fact less than or equal to the upper sum. So here, remember that the n is the number of rectangles. So depending on how big n is, so you can in fact get a better approximation of the area here. So you can pause the video at this moment and then just plug in certain n values, n equals 3, n equals 4, n equals 5, and see the lower sum and upper sum, what they are. You can just find them out. And you can get a good grip of what the actual area could be in that circumstance. All right, in this slide, we're talking about the limiting process, as I promised in the learning objective. So this fact says that if you have a continuous and non-negative function to start with on the closed interval a and b, so when you pass the limit, meaning that you let n go to infinity for both lower and upper sums, so these limits exist and they are equal to each other. So what that means is here when you pass the limit for the lower sum and for the upper sum, so these two limits are equal here. In fact, remember that delta x is the length of each subinterval, so these are the widths of inscribed or circumscribed rectangles, and f of little m sub I, f of capital M sub I, these are the minimum and maximum values of the function on those subintervals. So one provides you the inscribed rectangle and the other one provides you the circumscribed rectangle. So we're going to use this fact, in fact, to find the actual area of the region after we pass those limits. All right, here we go. So in this slide, we talk about like finding the area between f and the x-axis and the vertical lines x equals and ax equals b. So in this particular case, we're trying to show that you don't need to get the minimum or maximum values of the function, but you can actually, in fact, pick any point in each subinterval and look at the function value here. So the rectangle corresponding to that doesn't need to be inscribed or circumscribed, so it could be a rectangle corresponding to that interval. And if you look at the height determined by CI, then you would also get closer and closer to the actual area. And in fact, if you pass the limit as n goes to infinity, meaning that you're putting as many rectangles as you can, so the actual area is represented by that limit. So in the previous case, remember that the heights of those rectangles were determined by the minimum and maximum values of the function. So in this particular case, we're just saying that you can pick, in fact, any CI, any point from each subinterval to determine the heights of each rectangle. And once you pass the limit, you still have the area of the actual region. All right, let's go with an example here. Let's say like we have f of x equals x cubed. The area mentioned in this problem is the area between this curve x-axis and the lines x equals 0 and x equals 1. So it's the pink region here, as you see. So what are we going to do? Well, first we're going to find delta x, obviously. So since the interval is 0 and 1, we're going to divide that into n subintervals. So it's essentially 1 minus 0 divided by n. Endpoints, take the difference between the endpoints divided by n. So this is going to be the length of each subinterval. And based on the definition of the area, as I just told you, you can pick any x within the ith subinterval. For that reason, well, why don't we pick the right endpoints? And you can pause the video at this moment. You can change that to the left endpoints if you want to. That would be the case like CI equals I minus 1 over n. Again, if you go with the left and points, okay? So it's totally up to your taste at this moment. Going with the right-hand points, CI equals I over n. So f of CI is going to be the height of each rectangle, and delta x is going to be the width of that. And if you take the summation of the product of these two numbers, that's going to be the area, the total area represented by those rectangles. So eventually, when you pass the limit, when you let n go to infinity, that means you are getting infinitely many rectangles and infinitely many subintervals, obviously, to go with. And the actual area is coming out of this limit process. So here we go. Let's calculate this sum here. So f of CI for CI equals I over n, and for f of x equals x cubed is going to be I over n cubed, and delta x was just 1 over n already. So it's equal to I cubed n cubed times 1 over n here, right? So essentially it's I cubed divided by n to the 4th. And here you can pull out 1 over n to the 4th, so it's independent of the summation process here. I'm not pulling that out of the limit, by the way. Be careful. I'm just pulling it out of the summation here because I still have the limit on n. So now to find the sum, use the summation formula. So this is the sum of the numbers cubed, I from 1 to n. So and it comes with the formula n squared, n plus 1 squared divided by 4. So now this is multiplied by 1 over n to the 4th. So let's expand this out real quick. So this is 1 over n to the 4th, n squared times n plus 1 quantity squared, which is n squared plus 2n plus 1, all divided by 4. And in fact, that's equal to 1 over n to the 4th, n to the 4th, 2n cubed, n squared divided by 4. Okay? So in the next slide, I'm going to show that to you. There we go. And if you distribute 1 over n to the 4th all over the terms, you have 1 over 4, 1 over 2n, 1 over 4n squared. So now I'm going to pass the limit, and going back to the limiting process here, as n gets larger and larger, obviously these terms are going to approach 0. Only 1/4 is going to survive here. So the limit takes you all the way to 1/4 for this particular case. So that's in fact the area between the curve y equals x cubed and the x-axis stuck in between 0 and 1. So it's the area of the pink region to be exactly equal to, not approximately equal to, but exactly equal to 1 over 4. So in this regard, you can actually go back to the previous example that we had, and you can pass the limit for the lower sum and upper sum to find the actual area. So let's say like if you go with upper sum here, so limit of the upper sum as n approaches infinity, well, you have those terms tending to 0 as n gets larger and larger, so this is going to be 8 over 3. And if you go with the lower sum to start with, because we can start with any sum based on the theorem that we just mentioned here, so if you go with the lower sum and pass the limit, again, these terms are going to approach 0, and the actual limit is going to be 8 over 3. And in fact, this is the area between the curve y equals x squared, stuck in between the vertical lines x equals 0 and x equals 2. Okay? So this actual area, not inscribed, circumscribed, but the actual area is represented by 8 over 3. All right, I'm going to finish this video by the last property here. You can use the midpoint rule, in fact, from each subinterval. So you have xi minus 1 and xi. So normally we choose either left endpoint or right endpoint, or depending on the description of the function, increasing or decreasing on that interval, we go with like minimum or maximum values of the function. But there's an alternate way to handle that. You can also choose the midpoint from each subinterval by, in fact, looking at the average of these two numbers. And the average is the sum of these numbers divided by 2. So you can actually pick your CIs to be exactly equal to this, and this is again called the midpoint rule, and the heights of each rectangle is determined by the midpoint, the function evaluated at the midpoint. So this is sort of like another approximation essentially that you can go with. So you may have a couple of exercises for you to go through after you watch this video. One of them is like f of x equals cosine x, and then you have the interval 0 pi over 2 using the left and right endpoints for each subinterval with 4 rectangles. The question is asking you to approximate the area between cosine x and the x-axis, as you can see in this picture. So please do it after you watch this video. This is one example. And another example that I have here is that find the area between the curve x squared minus x cubed on the interval -1 and 1 by using the limiting process. So essentially you're going to either write the lower sum or upper sum or midpoint rule, whichever the rule you want to go with, and you're going to write one sum, which is going to be representing the approximation depending on n, and eventually you're going to pass the limit meaning that you're going to let n go to infinity to find the actual area. Okay, so this is in fact x squared minus x cubed with n equals 4 rectangles and maybe 10 rectangles, but you're going to write the lower sum or upper sum for any n, so that at the end you can pass the limit. In other words, you can let n go to infinity. Okay, let me see if I have another example here. One more example. Using the midpoint rule for n equals 4, the question is asking you to approximate the area of the region bounded by x squared plus 1 over the interval 0, 2, and eventually the question is asking you to use the limit process to find the area of the same region. So that means you're going to use the midpoint rule for also n rectangles rather than just 4, right? But this is what you need in the first step. So hopefully, after you pass the limit, you're going to find the actual area of the region. All right. So this was a little bit a longer video, but there's a lot to cover. So I hope you weren't bored of watching the whole video. Please do those exercises after you are done with this video. All right. So thanks for watching. I'll see you in another video. Bye.